Hello, and thanks for joining me for this presentation on geomorphic field plots for monitoring stage 0 restoration. My name is Sarah Hinshaw. I'm a PhD student at Colorado State University in the Department of Geosciences. I study fluvial geomorphology with Dr. Ellen Wohl. Right now, my work is on carbon storage, and I will be surveying different stage 0 restoration sites throughout the state of Oregon and Colorado for my PhD dissertation. Last summer, I worked out of the Pacific Northwest Research Station in Corvallis to develop the field-based monitoring plots at the South Fork McKenzie River Stage 0 restoration site. Stage 0 effectively resets the valley bottom, and the addition of wood creates the hydraulic and geomorphic complexity that benefit habitat. So the process-based restoration is allowing this wood to naturally fill out jams and create pools and naturally evolve to the anastomosing planform. Our monitoring strategy pairs geomorphic on-the-ground field plots with remote sensing plots. The goal is to calibrate the remote sensing data with the ground measured data, and then in the future validate that remote sensing by repeating the ground plots again. And once we have this validated enough, we can eventually repeat it in a more long-term sense using the remote sensing methods after we establish those relationships with on-the-ground data. This will allow us to assess change over a longer period of time than we otherwise would be able to. The first step in the geomorphic field plot method is choosing the locations for where you'll put your plots. To create an element of randomness for statistical analyses, we randomly selected GPS locations using a random point generator in GIS. And to create the boundaries of where we would put those plots, we mapped the area that was inundated at the highest flow. So in our case at South Fork McKenzie, that was 5,000 CFS. So at this flow, we mapped the area that was inundated, and then that's how we differentiated the in-channel plots and then the forestry plots, which were in the forested floodplain outside of the inundated area. So we kept everything pretty simple. We thought about stratifying the valley into different geomorphic units, but with stage 0 restoration, the adjustment is going to change the channel planform so fast that creating strata would just cause the need for changing those strata later on, which is why we only kept the inundated area at high flow versus the dry area. And so the plots were randomly distributed throughout the inundated area. And at South Fork McKenzie, we had a total of 40 field plots. And each one of these field plots would represent a 40th of the total area that the phase 1 of the project, which we measured, took up. This is a conceptual diagram of the geomorphic field plot layout. So notice that there is a center subplot and 3 exterior subplots. Each of the plots is separated by 3 meters, and the center subplot only has one different measurement than the exterior subplots. The only difference is that you would measure large wood volume at the center subplot and not at the exterior subplots. We did this because at the South Fork McKenzie River site, there was a huge amount of large wood that was pretty consistently distributed across the floodplain. So it was taking a really long time to measure large wood at all of the exterior subplots too. However, for future use of the geomorphic field plot method, I do recommend that you also measure large wood at the exterior subplots. And I'll go into specific measurements in the following slides. For setting up the plots, after you measure your center subplot, lay out a tape for 3 meters in the 30, 150, and 270 degree azimuth directions. And these just create a consistent orientation for the field plots, and they also allow the exterior subplots to be evenly spaced from each other. All of these subplots are 1 meter radius. So sometimes it helps if you have a rope with you to actually lay out that 1 meter radius circle so that you can accurately visually assess the percent of wood coverage, which I will explain on the wood slide. Our geomorphic field plots are a hybrid of forestry and geomorphology field methods. And these plots will be paired with photo plots that are captured from a drone. The photo plots can allow us to estimate the area covered by wood at a particular site. We can use the photos to assess the sediment size distribution, although it's been proven a little bit difficult to get the really small size sediment from images. Videos that are taken at the same location as the photo plots and the geomorphic field plots can help us measure velocity and get a variance of velocity across the entire site, which is important for habitat assessment. Drone data can also help us create DEMs and assess how the actual topography of a site is changing over time. And lastly, I'll just mention that we had a thermal camera on our drone, and capturing this temperature data of just the surface of the water from the drone, that can be compared to the temperature data that we get from hobo temperature sensors that we installed at each geomorphic field plot. Just to reiterate, this presentation is only about the on-the-ground geomorphic field plots, but if you have questions about the photo plots, you can contact Matt Barker or Jonathan Burnett. This is a list of materials that we used to collect data at the geomorphic field plots at the South Fork McKenzie site. We recorded all of our data with a Samsung Galaxy tablet that was paired with an Arrow 100 GNSS receiver. We got about 3 centimeters accuracy at each plot, and those are very helpful for recording the plot center, especially if you're following up with a photo plot study. We used a TruePulse 360 laser rangefinder to mostly measure the length of large logs that were placed, and this made it a quick and easy measurement. We used engineer's rules to measure the water depth, although you can use any kind of tape measure for that. And then a diameter tape, we used one that was in metric. We used that to measure the diameter of the large wood at the center subplots. We specifically measured the diameter at the center of the log, even if that center of the log didn't fall within the 1 meter radius subplot. We used a gravelometer to measure sediment size, and that was very quick measurement. And then we used just a normal tape for measuring that 3 meter distance from the plot center to the subplots. We used a Marsh-McBurney FlowMate velocimeter to measure velocity at the surface and at 60% depth, and a densiometer to measure canopy cover. A compass is required in the field to set up the plots and find those azimuth directions for the exterior subplots. And then if you decide to measure temperature as well, we installed hobo temperature sensors during low flow, and they were submerged at the time we installed them. We tied them with P-cord, and we always had a knife with us to cut the P-cord and then tie the temperature sensor onto a stable object. It was useful for us to have a waterproof fanny pack because sometimes you accidentally end up swimming. We use the Avenza app on our phones and the tablet to help navigate to each plot location. Our site was really large, so this was very helpful. We had an inReach Garmin GPS with us too. That helped us navigate to the plot locations, and also with the inReach capability, it was an extra safety feature. And then the Seek app, which is by iNaturalist, helps to identify vegetation that's nearby. And so that would just be something we recorded in the notes at each field plot. Okay, so one of the main things that we measured was wood. We measured large wood and coarse particulate organic matter, CPOM, and also in the method that we used where we estimated percent coverage, this also includes fine organic matter too. So for large wood, we measured the diameter and the length of any piece that fell within the center subplot. And like I said before, I recommend that you also do this in the exterior subplots for future use of this method. We used the diameter tape, called D-tape, to measure it at the center of the log. Like I said, even if that center is not within the subplot, go to the center of the log and measure it, because that's the most representative point if you are calculating the volume of that particular log as a cylinder. You can go into more intensive methods of measuring logs. I know some foresters do, of measuring the crown and the root mass, but we were trying to do this pretty quickly, so we just calculated the volume of the wood as a cylinder. For the CPOM, coarse particulate organic matter, we estimated the percent coverage of organic matter within each 1 meter radius subplot. So this is really fine woody material, and then the woody material that does not meet the criteria for large wood. This is our way of incorporating that into the study. Last year, since we did not include large wood in the exterior subplots, we included, if there was large wood at the exterior subplot, we included that wood coverage into the percent coverage estimation of the exterior subplots. But if you choose to measure large wood at all of the subplots, then you can do those separately. I recommend that you record a thickness of the organic deposit of coarse wood that doesn't meet the large wood criteria, and that way it'll be easier to calculate a wood volume at the entire site. So let's talk a little bit about how to estimate that percent coverage. Like I said, it would be ideal if you actually had something laying out that 1 meter radius subplot, but once you train your eye to know how big that subplot is, it's not always necessary to do it, especially if you're trying to be quick and efficient. So it's important before you go out into the field to train your eyes on what percent coverage looks like. And I've added this diagram, which I just got somewhere on the internet, that's showing how much coverage is each percentile of how much of the area is covered. And so in our case, this would be covered by fine sticks and any type of coarse organic matter. For sediment, this photo is not actually in the South Fork McKenzie, but it's a very happy field assistant measuring sediment. So we used a gravelometer, and many of you already know how to use a gravelometer and measure sediment, but I'll just go through it really quickly. If you pick up a class, it's got 3 axes that are all perpendicular to each other. The A-axis is the longest axis, and the C-axis is the shortest axis. So basically the thickness of that class, and the A-axis would be the length of that class. So the B-axis is the intermediate between the two. And this is what we want to measure with that gravelometer, or if you choose to measure with an engineer's rule, that's fine too. The gravelometer makes things really quick and easy because all you do is pass the clast through the holes in the gravelometer, and it acts like a sieve with really large openings. So pick up a clast from the ground randomly. You don't want to bias your measurement by picking one out before looking at it. And because our subplots are only 1 meter radius, they're pretty small, we just did kind of look away and then the tip of the boot method where you look away, you pick up the sediment clast that's touching the tip of your boot. And then you walk around the 1 meter radius subplot and pick out 10 clasts. So with 4 subplots, 3 exterior and 1 in the center, you'll end up with 40 clasts measured per subplot. And so you pass the b-axis of the particle through the hole in the gravelometer. You record the first hole that it fits into, or the smallest hole that it fits into before the clast is too large to pass through. There are several resources on this method online, and Kristen Bunte has what we call the Sediment Bible, where she has a 400-page volume about every possible method of measuring sediment. So I encourage you to check that out. She's based out of Colorado State. And so when you're writing this in a field notebook, you might use a tally method to record the size of each clast. We had a survey where we just picked an option for the size of the particle in our survey 123F. And ultimately you will get a sediment size distribution for each plot and for the entire site if you want to. And then this will be really useful later on because you can actually quantify the sediment size distribution change over time, which has implications for habitat. We also measured hydraulic data at each subplot, and so that is velocity, water depth, and then I added water temperature in there too. For velocity, make sure to measure at the surface and at 60% depth. We used a Marsh-McBurney velocimeter to measure velocity, and we took an average of the measurements over a 10-second period, or just wait until the velocimeter stabilizes in your velocity and then record that number. There are several settings on the Marsh-McBurney where you can set it to average by itself, or you can do it with the instantaneous measurement. For water depth, we use the engineer's rule because it stays rigid in if you're standing in flowing water, so it can make it a little easier than a normal tape, but either one would work fine. For the 60% depth, this is how you will get 60% depth, is by measuring the water depth beforehand. For the temperature sensors, we installed them in the subsurface during low flow conditions so that we could ensure that they stay submerged when the flow gets higher. And we installed one at every plot center. So we had a total of, we should have had a total of 40, but I believe some of them got placed elsewhere outside of the plot locations. Next is canopy cover. So this was adopted from a forestry method and is actually very useful because the vegetative cover of a field of the stage 0 site is going to change a lot over time, especially as the water table rises. So we had a lot of deaths of cottonwood trees, and then some Doug firs were dying as well. So this is an important thing to measure over time, because as you get those trees dying, you also get new recruitment of wood to the channel. We used a densiometer for this, and the way that you use a densiometer is by calculating the percent coverage of the canopy by averaging densiometer measurements in each cardinal direction. You count the number of intersections on the grid that's on the densiometer, and then that number is what you record, and our app calculated the average for us. So for our particular densiometer, there were 17 total intersections, and so if we measured 17 were covered by trees, then we had 100% canopy cover. And again, we average this by facing. You stand with the densiometer open in your hand and you level the bubble on it, and then you face each cardinal direction and take an average. This happens at both the center plot and all of the exterior subplots. It's really important to note any geomorphic observations. We did this by identifying the geomorphic unit that we were standing in at each plot, and our options were a wet meadow, which, as you can see in this photo, it has some beaver activity, so that's something important to note too, because beaver create a feedback of raising the water table even more and pooling water and slowing the velocity. We also identified flooded forests, riffles, pools, runs, and a lot of other geomorphic units. So this wasn't a choice that we picked from. It's something that we wrote independently for each plot. And then we also left a space to add any notes and geomorphic observations. So this is kind of a fail-safe plan to just document the plot where you're standing and notice your surroundings. I personally think that this is really helpful for field personnel too, to just get a better understanding of heterogeneity and the site itself. Forestry plots were measured in the dry areas of the treated area, and they actually happened after I left to go back to school during the summer. So again, for information about forestry plots, contact Jonathan Burnett, Katie Nicolato, who is another student at Oregon State, or Matt Barker. And these are basically to assess the change in species, coverage, and size as the project evolves. Don't forget to always take your GPS point and a photo of every plot. So in this picture you can see Katie Nicolato with our friend Raina the Raven helping out with the GPS measurements. We waited. If our GPS, our Aero GNSS receiver, was getting poor accuracy, we just stood there and waited until it got 3 centimeter accuracy. So just a quick note about safety. In some instances, we encountered plot locations, because they were randomly located, you never know where they're going to be. We encountered some plot locations that had water that was too deep to safely measure the metrics that we wanted to. In those cases, you make a special note and measure what you can and then visually estimate the rest. Walking on logs can be a challenge, and it could potentially be dangerous if you don't have great balance, although you'll definitely get better balance throughout the field season. But just be very careful walking on logs and wear shoes with really good traction. In general, don't work alone in these types of sites, because there are quite a few hazards, especially with the walking on logs. The InReach GPS that we carried around with us gave us another layer of safety in the methods that we were doing out in the field. And then always bring a first aid kit. This is a summary table of all of the methods involved for each metric of the geomorphic field plots. So it says the category of measurement and then whether they're at all of the subplots, exterior and center, or just the center. And again, I want to reiterate that a suggested change would be to measure the large wood at all 4 of those. subplots. There are a few other suggested changes in the column to the right, and it's up to you all whether you choose to adopt those changes or not. I realize that each site is different and many modifications might need to be made to this method, but I'm excited to share it with you and thank you for having me. One issue that we've been having is how to organize our data and how to carefully associate each plot's data with its correct location. And that's just an issue with the Survey 123 app, but it can be resolved. We just haven't quite figured it out fully yet. Thanks for listening and good luck with your geomorphic field plots.